Welcome. Today, we'll solve an interesting problem about the Earth's atmosphere. We want to find out, how high would the atmosphere extend if it had a uniform density equal to zero point 0.4 times its current density at sea level? Let's first visualize what we're dealing with. Here's the Earth, and around it is our atmosphere. In reality, the atmosphere's density decreases as we go higher. It's more dense near the surface and gets thinner as we go up. But in our problem, we're asked to consider what would happen if the density was uniform throughout, specifically at zero point 0.4 times the density at sea level. To solve this problem, we'll use the equation for pressure due to the weight of a fluid column. The pressure at the bottom of a fluid column is equal to the density of the fluid times the acceleration due to gravity times the height of the column. Let's list our known values. The pressure at sea level is 1.013 times 10 to the fifth newtons per square meter. The density of air at sea level is 1.29 kilograms per cubic meter, and gravity is 9.81 meters per second squared. Since we want the uniform density to be 0.4 times the sea level density, we multiply 1.29 by 0.4 to get 0.516 kilograms per cubic meter. Now we can rearrange our equation to solve for height. We'll move density and gravity to the denominator. Let's plug in our values. 1.013 times 10 to the fifth newtons per square meter divided by 0.516 kilograms per cubic meter times 9.81 meters per second squared. When we calculate this, we get approximately 20,000 meters or 20 kilometers. To put this in perspective, this is about twice the height of Mount Everest and about where the stratosphere begins in our actual atmosphere. In reality, our atmosphere extends much further because its density gradually decreases rather than suddenly stopping. The actual atmosphere extends hundreds of kilometers into space, becoming increasingly thin. This example shows how mathematical models can help us understand physical systems, even if they're simplified versions of reality.